mechanisms occur, what kind of elasticity governs the behavior, what's the dependence on sequence, and these kind of things that you can really get into the details of using molecular simulation approaches. So I mentioned these different kind of experiments, atomic force microscopy, and optical traps. Here you can look at, for instance, motional and molecular model, and you can try to do the same with the simulation at larger length scales. And there's many more recent methods where you can really observe unfolding and folding events, such as a thread or other types of approaches where you get higher resolution. And then when you look at simulation, you have almost infinite resolution, except for the electrons, where you can really get the individual bonds breaking, their functions as a function of time, and you can really see unforeseen mechanisms of how proteins can unfold. You can really zoom into a protein and look at some of the basic principles. And in this sense, it's very similar, as we said, to experimental approaches. Instead of a cantilever, you can have a spring and you can stretch the molecular system. So we mentioned that hydrogen bonds stabilize proteins, and there are two kinds of proteins that are very commonly observed in nature. One is called beta sheets, the other called is alpha helices, and they have completely different topologies. So one is more like a sheet-like structure. So you have these clusters of hydrogen bonds that basically go on top of each other. And depending on the direction of the strand, you can either have parallel sheets or anti-parallel sheets, strands. In the case of an alpha helix, it's more of a helical structure, so it gets localized. These localized interactions make the protein coil into this helical structure, which typically has a certain length and certain diameter, so it's preserved across almost all proteins. And one of the things we want to understand is how these hydrogen bonds break. I mean, we had this simple theory that we talked about. We can also compare these with experiments and study how the bonds break and what are the key factors that govern their mechanical properties. And this is not only important for proteins, but also important for a lot of polymeric materials we use in real life. Something like Kevlar also has these hydrogen bonded features. So anything you find from fundamental studies on hydrogen bonds could be applicable in theory to other materials. And you can see different kinds of mechanisms here. In the case of the helix, which is a sheet where you can have a slipping of the system. So we've done a lot of different studies. I'm not going to go into the details, but a lot of this is published. And there's certain things that we consistently observe across the protein universe. And one of these is a strong dependence on rates, and also strong dependence on the geometry of loading. And with the rate effect, there are basically many reasons, but typically the reason is we're running simulations in non-equilibrium, and even experiments are done in non-equilibrium to a large extent. And in reality, a lot of physical situations where we have injury or shock, etc., these are also done in non-equilibrium rates. So this is part of the deal. The question here is, can we really characterize how this rate dependence is manifested in these materials, and what are the basic mechanisms that lead to the rate dependence? And there's been many studies looking at solvent viscosity and mobility, thermal contribution to rupture of weak bonds. So essentially, if you wait longer, you have more thermal vibrations that might probabilistically cause the bond to break at some point. And there's also geometric effects. So if you look at the helix scenario, if you pull the helix really fast, it might start unwinding from one end, and it can have a scenario of almost like a shock. In the other case, if you have to do it really slowly, it might unwind it at a random point and then propagate from that point. So there are many differences looking at the different rates. And we've done a lot of simulations trying to bridge the difference between experiments and simulations. So experiments typically are done at very, very small rates, whereas simulations are done at very high rates. Especially the early simulations in the area were done at extremely fast rates. And what we observed in many systems is that as you try to go and bridge these orders of difference in magnitude in pulling rate from time scales, you go through many different energy landscapes. So in the case of a helix, if you pull it very fast, you might have bonds breaking one by one, whereas if you pull it really slowly, you might have initiation at different points. and that pertains to different kind of energy landscape that you probe. And the idea is we have to pull at certain rates to be really close to what we consider experimental energy landscapes. And we still don't know how many transitions you can have here, but for sure there are certain rates that give you results that are extremely different than experimental rates. But with more simulation power, we've come closer and closer to some of the measurements we can do experimentally. And it's the same with experiments. Experiments are getting faster too, so eventually they're going to converge, but I don't know how long that will take. And then we'll have the whole landscape of rupture forces as a function of rate. And that would be an ideal thing for many different high-strain rate applications, also applications. The other effect that we observe is a strong dependence on geometry. And again, you look at different energy landscapes or different energy values that you're hopping over when you pull things differently. So this is very much similar to what you observe in continuous scale, in the sense that if you have hydrogen bonds and if you try to shear them in one direction, they can give very high energy barriers. In the case of another scenario where you try to tear them, so if it's like tearing a piece of paper, you don't have a very high energy barrier, so you don't get a very high resistance to force. So what you observe in many mechanical proteins is that the hydrogen bonded domains are oriented with the typical loading direction of the material, like in a fiber, if they are oriented with the fiber direction. And this is particularly important for spiders, as I will explain later. So there are many different things people look at. I mentioned cellular and subcellular mechanics, so looking at what happens within the cell and the different length scales and different kinds of proteins. So I mentioned microtubules. These are almost like columns in a cell. They are very rigid, mechanical. We have actin filaments, which are tensile members, very stretchy materials. And then we have intermediate filaments, which are somewhere, as the name implies, somewhere in between in terms of rigidity. And there are many different groups that try to understand every single aspect, every single kind of protein that exists within the cell and that relates to the function of the cell. And then there's many other studies looking at extracellular matrix, so what is outside the cell and what we consider connective tissue. So it could be cardiovascular system, it could be bone, it could be collagenous tissue, and so forth. And many different types of collagen exist in connective tissue, and it's a very important material for scaffolding, as I mentioned. And then you can also mineralize it with, as in the case of bone, to create different kinds of material with different properties, such as very high toughness. And then what we've done in the past is really try to understand how atomistic simulation can shed light on the mechanisms of unfolding and elasticity of collagen. So there are many diseases where molecular changes in the collagen can play a role in the mechanical properties of the material and its assembly properties. So this is some of the work done by Alfonso Gautier, who was a former lab mate. And this is related to what we call osteogenesis imperfecta, which is called the brittle bone disease. It's a mutation that causes changes in the structure of the bone. The exact mechanisms are not very well known, and there's probably several hierarchies that play a role here. But some of the work done in this area with molecular dynamics is understanding how collagen fibers or fibers or molecules assemble into larger scale fibers, and how a mutation would basically play a role in the interaction energy between these molecules. So you would look at the binding energy between molecules, and if you have a lower binding energy or a lower modulus, that would mean that there's some difference in the anisotropic mechanical properties of collagenous material. And then there are some correlations that we can see with severe cases versus regular cases with regards to mutations. And you can also have basically a difference in the binding energy, where in some cases you have, if you think of the Leonard-Jones kind of interaction, you have basically a dip, which is good because you have a reference state or attraction. In other cases, you just have very little attraction or no attraction, that they just don't bind to each other. And this basically is an important consideration looking at self-assembly of collagen in tissue. So if you have, let's say, bulky amino acid that replace what's supposed to be a small amino acid, the packing of the molecules will change and the interactions also change, and that can cause disassembly and severe diseases. Now, this is not only for brittle bone disease, we also looked at diseases related to kidney, where type 4 collagen also has some mutations. And then we talked a little bit about what happens within biological systems, within our physiology, but there's many applications where we can look at things outside the body as well. And one example is the work we've done on spider silk, which is, as I mentioned, a very tough material, very interesting material from a mechanics perspective. And there's many hierarchies in this material as well. So you can start from electron density of the hydrogen bond beta strands, and then you can look at beta sheet nanocrystals, which are embedded in this amorphous material. So it's like almost like a composite material, but both phases are made up of proteins essentially. And then these become silk fibrils, and then fibrils become the core of the material, and then you have basically many different hierarchies. And at the very end, you have this interesting material, the spider web, that behaves very favorably in a mechanical perspective. So the idea here is, can we break this down into simple constituents and try to understand every single constituent in a lot of detail? And one aspect here is the beta sheet nanocrystals that I mentioned. These are repeats of polyamine or polyglycine alanine, and this is conserved across species, so it's always the same case with spider silk and commercial silk, any kind of silk, has the same repeat in these crystals. And the crystals are very important because they are basically what we call physical crosslinks in a polymeric material. So the more stronger they are, the more strength you can get out of the material. And then, but the mechanisms of failure has not been studied in detail for the specific case of silk. So this is one thing we looked at. And then the other thing we looked at is understanding these semi-amorphous regions. So regions where it's very hard to do structural characterization. We have a rough understanding of what the structure is, but they are extremely important because they provide extensibility to the material and toughness to the material. So the question there is, how do you start off and find out the structure, and then can you do any mechanical characterization of that structure you achieve in silico, and whether that would relate to actual mechanics. So I will talk briefly in the last 10-15 minutes I have about the mechanics of these protein nanocrystals. So in the case of spider silk, what you have is basically these polyglycine alanine or polyamine repeats that stack up and cluster into these hydrophobic domains that form these crystals. So these are very short in length scale, usually 6 or 8 residues on average. And then basically they are interlocked by these hierarchies of, by assemblies of hydrogen bonds. And then what we did in this simple scenario is what we would like to do in a lab, but we can't because the crystal is extremely small. Basically do different kinds of mechanical tests to get an understanding of how this crystal would behave when you apply forces to it. And one of the tests we do is basically create an assembly of the crystal and then do a bending setup. So these are very rigid crystals, so when you do a bending, it's almost like a cantilever beam. And then you can also do a pull-out setup where you have this crystal and then you try to pick one strand and basically pull it out and see how much it adheres to the other strand. So this is almost like a pull-out test you would have for concrete, reinforced concrete, and so forth. But occurring at the time length scales of nanometers, very small. And then these lateral shear conditions, as I mentioned, is relevant to silk because in silk you have the fiber is drawn, so you have very good alignment with the direction of the fiber. So when you stretch it, you have strands that are sliding past each other. Okay, so from the bending simulations, you can observe several things. You can apply a force, you can measure the deflection, and then from that force deflection curve, you can basically fit Timoshenko beam theory, and you can understand at which length scales you have more of a shear dominated behavior, and at which length scales you have more of a bending type of beam, an oidal type of beam. And You can also, by fitting into these equations, you can also get elastic properties of the material, which are of great interest for experimentalists as well, since doing tests on individual crystals is very hard. I mean, it's only a few nanometers, so you can't really do it with AFM very easily. So what happens in many experimental studies is that they try to infer the crystal modulus by looking at the overall modulus and then looking at volume fractions and then making assumptions of uniform strain or uniform stress and then getting an effective modulus. And this is why there's a huge variation in the Young's modulus values typically reported in experiments. So in this case, we got something in that range, but we don't know, of course, whether it's supposed to be 16 or 28, but overall there's some good agreement with experiments. And then we also looked at shear modulus of the material, and shear modulus has never been studied from the crystal perspective, but from the material perspective, it's again in the ballpark. But we'll see, I suppose, more experiments where people will look at these materials at smaller scale. And then the other thing we did was these pull-out simulations, and we observed some interesting things here. We can change the size of the crystal and look at how the pull-out mechanisms vary as you change the size. And when you change the size from just a few nanometers, let's say 1 or 2 nanometers to 5 or 6 nanometers, you have a huge difference in how the system breaks. In the case of the small crystals, we have basically one strand getting pulled out, and it can basically stick back to where it was by sliding through a slip mechanism and reforming the hydrogen bonds. In the other case, you have more of a crack-like formation. So as you stretch the system, the hydrogen bonds at the pulled end stretch more than the ones that are at the far end, so almost like a beam. And what this causes is basically you have very little cooperativity between the hydrogen bonds. So if you look at the strain distribution across the crystal, you have a sort of a strain concentration at the front end, whereas as you shrink the crystal size, this basically becomes negligible. So you have more cooperativity of hydrogen bonds when you look at smaller crystals than when you look at large crystals. And you can look at you can basically measure the strength values and compare it to mean and run many simulations and look at the pull-out strength, and it seems to diminish as you make the crystals larger and larger. But looking only at the nanometer scale sizes, very small crystals. You can also look at the total amount of energy you dissipate, and also that will shrink as you go higher in that scale of the crystals. And here there are two factors. One is, of course, the value of the strength, but the other factor is the fact that it can rebind. So if you have two molecules that are stretching and rebinding and stretching and rebinding, this is a very dissipative process, so it would be very favorable for a polymeric material to have this rebinding capacity. So the idea here is basically we're trying to discover the secrets of the spiral silk, what could be the reason for its toughness. And one of the interesting experimental observations is that most of these crystals are indeed in the order of a few nanometers, and by modulating the crystal size very slightly, or only in the order of a nanometer, you have a huge difference in the mechanical strength. There are multiple mechanisms to this, one of which is, I think, this mechanism we found out that you have basically different failure initiation mechanisms at small scales. And of course, there might be other reasons at hierarchical levels with regards to how you create interfaces and so forth. But one of the key ideas is that since you can't have cooperativity with hydrogen bonds as you make the strands very long, you need to make the strands very short. And then because strands are very short, that means as you stack more strands in sort of like a pancake kind of system, if you apply a force to it, because you don't have an infinitely larger width, you basically can't increase the length very high either. So you basically have to confine the system into a nanometric dimensions with both a small width and a small height. And when you do that, you get both a strong and a tough and a resilient crystalline system. And this is the basis of what we think is a very high strength for a material that employs actually weak bonds, like the hydrogen bonds, which are order of magnitude weaker than even the weakest covalent bonds. So that's the main difference that we think is the case for this material. And it's worth to mention why this is really important. I think in this case, LMST simulations can really shed light on certain mechanisms in conjunction with experiments, where we can provide molecular descriptions of fundamental assembly mechanisms and fracture mechanisms at the same time. What we observed in the case of spider silk is that you have basically very simple amino acids. Lysine and alanine are the simplest two that exist in nature. Chemically, it's basically a side chain of a hydrogen and a side chain of a CH3 group. There's nothing complicated with its chemistry. But by conserving these hydrogen bonded domains and by structural arrangement that is very clever, then you can get a very high toughness and strength and even possibly self-healing capacity by the stick-slip motions and so forth. So the idea here is that you could really have simple and universal features such as the backbone hydrogen bonds, but if you arrange them and process them in a certain way, then you could get very interesting mechanical behavior. And the idea here is basically we want to illustrate the mechanisms of utilizing these weak bonds to their maximum capacity so that we have what we call a nano-confinement effect of these crystals, and then basically you can get very high strength and toughness at the same time, which is quite counterintuitive in many cases. And this is a key role of the self-assembling material. So if you have covalent crosslinks, this doesn't happen very easily because you can't really switch them and you can't really reform them very easily. And they behave, based on the theory, they behave more individually than weak bonds, which behave more cooperatively when you make them into nanoscopic assemblies. So this I think is one idea that could be exploited for bio-inspired materials. And there are groups that are doing this, that find similar observations with size of terms of weak bond clusters. I believe that's all I have, but I think we can discuss a little bit any questions that you may have.
You were stretching experiments on proteins. Did you do some kind of loading and unloading kind of experiments?
I haven't, and I think it would be very interesting.
Do you expect some kind of hysteresis behavior?
Yes, I would expect hysteresis, but the other issue is if you pull fast, then it won't be reversible. So you want to look at thermodynamically reversible processes. You need to play certain tricks to look at basically loading and unloading scenarios. So there are ways to look at non-equilibrium simulations and look at the equilibrium level hysteresis effects, because it's very rate dependent, like this hysteresis effect. So if you want to compare with something like dissipation in experiments, then you would have to bear in mind that there's a very strong rate dependence effect. So people usually use something like a Jasinski's inequality, which is a thermodynamical description, an approximation in this case, to get that behavior at different rates. But yeah, I would expect something basically like this, where you have some stretching, and when you come back, you can dissipate this energy because you're breaking a lot of weak bonds and what we call sacrificial bonds that cause this behavior. But depending on the geometry, if you have two chains that are hydrogen bonded like this, and then if you stretch them apart and if you break them apart completely, then it won't come back in any near time to be assembled. It will eventually reassemble. But
for instance, in your crack like mode 1 like behavior, so you open half of the crack and then again close it.
Yeah, I mean that can rebind, yeah, exactly.
Then in those situations it can reproduce the same behavior forever.
Yeah, I think so. At least for indices we've observed that kind of behavior, but we haven't done the same data sheets. It's a good question.
Can we go back to the hydrogen? You showed the strengths of a peak at the 4 bound.
This?
Yeah, yeah, here. You plot the shear strengths, right? That's some failure force
Yes.
and divided by the area.
Divided by
Are you sure there's a strength even at one bound? Is that right?
There is no strength in one bond.
But what is that zero? That's two?
Yeah, that's
But
actually-
even with two bound, the lifetime is still finite, although it's bigger than one
Yeah.
bound. So this little, how do you define the strength at that point?
So
Because,
this is based on the Bell approximation. It may not be a very good approximation.
oh,
actually.
from Bell's approximation.
Yeah, so
Okay.
I mean, basically, it's even simpler than the probabilistic approximation in the sense that you say if you have n bonds and then an ED, and this becomes your effective energy barrier, which actually may not be the case because if you, not all the bonds.
Because
are the same.
yeah, because Schwartz, Woody Schwartz has done an analysis of that, showing the strength only emerges with sufficient number of bonds.
Yeah.
With two bonds, there's no strength.
There's no strength.
Right, the Bell's approximation, yes, I understand. Because
Yeah.
that's just equilibrium.
Yeah, I think that, yeah, I mean, there's multiple ways to look at it. This is just,
Right.
just
Yeah, yeah. I had a similar plot yesterday because it took a lifetime.
Oh, yeah.
Similar to
Yeah,
this,
yeah, yeah.
actually. We're talking
Yeah,
about similar
I think
things.
that's a
Yeah, yeah,
very nice
that's-
analysis, looking
Yeah,
at
yeah, yeah.
probabilistic and
Yeah.
considering rebinding and
Right.
so forth.
Probably it's better to plot as a lifetime in the, since you
Yeah.
only have a few bonds. Yeah.
Yeah, I mean, I agree, probably that's a bit.
Yeah. Okay.
But in the case of 1 or 2 bonds, we have zero strength, and once you go to 3, 4, 5,
Right, but they show some like two is zero, right? And three is finite.
3 is finite.
Yeah, but if you use Woody
It's
Schwartz,
in between 3 and
right, if you use the correct stochastic dynamic description of discrete bonds, then the strengths will not emerge for those few bonds.
few bonds.
And you need really a large number, sufficient large number.
Okay.
Right? If
But,
you read Woody Schwartz analysis, there's a 2004 PNAS.
yeah.
Yeah.
I know this paper.
Right. In Bell's model, he doesn't have that because they assume large number of bonds.
Yeah.
Bell started with the assumption of a huge number of bonds, and he only did the equilibrium analysis.
Yeah, it's very simplistic.
Yeah.
And our theory is almost deterministic fracture theory.
Yes, now I understand. Now I
Probabilistic
understand.
approach. So it's a very, I think that the whole motivation was to basically link elasticity to breaking of bonds, which
Yes.
no one at that time did for proteins, as far as I know. It's either you do the Bell type energy landscape approach, which has no elasticity,
Yes.
or the Mormon chain.
Right.
Just as a way to.
Yeah, well, we're addressing essentially the same effect. You
Yes.
assess that changes the stochastic dynamic at the peak,
Yeah.
at the optimal number of bonds.
Yeah.
But my point is, since Schwartz did this more accurate stochastic analysis, we no longer speak of strength only for 2 or 3 bonds.
Okay. Yeah.
Because the final lifetime is finite.
Yeah,
Right.
that's true.
But there is a critical number that strength seems to emerge.
Yeah. I mean, that's the basic.
Can you talk a bit about which kind of difficulties you find when you do molecular dynamic simulation?
So many difficulties. It takes 1,000 simulations to publish one simulation. No, I mean, in many cases, you try many different things and different boundary conditions, and you will find that certain conditions are not realistic, or doesn't work. And in some cases, you might have time scale dependence. In other cases, you might have force field dependence. It takes time to resolve all of these and then get confident with what you're.
Do you find any instabilities in the simulation before you get a good result?
Like numerical instabilities?
Numerical or something that you didn't expect? Because I suppose-
Numerical, I don't think so. Numerically, if you do it correctly, you don't get too many instabilities or things you don't expect. I mean, you will get a system blowing up if you use, let's say, a large time step or these kind of things. But if you're doing everything correctly physically, I can't think of many cases where we just can't get a good result. I mean, it's usually trial and error and you find the right choice to do. I don't know if that answers your question.
One slide you showed the comparison among experiments and simulations and basic functions simulation result. Usually, the density function calculation should be more accurate than MD simulation. But in your slide to show the MD simulation, the result in better agreement with the experiment results. So what do you think accounts for the results?
Well, I mean, for these soft matter, there's a lot of limitations with DFT as well, and molecular dynamics. But one of the key things is there's too many methods that can look at dispersive forces very well. I mean, there's more recent methods, and it's improving quite dramatically. But, and then you can do these calculations at zero temperature, which is high temperature. So it depends how you do them. And this was in this case, you have a perfect crystal. Everything is arranged perfectly. There's no dynamic defect formation, like bond breaking and reforming. So all of these weaken the system. So that's why you get a high modulus in both cases. In my but I mean, even if you think about it, if you match the experiment, that doesn't mean you're correct. It doesn't mean it just means you match the experiment. But the experiment itself might have a lot of errors in it. So I wouldn't say just from this picture that in all cases we're going to have better agreement with the molecular dynamics. It depends quite a bit on what you're trying to model. DFT is, in many cases, undoubtedly better than molecular dynamics, but in a lot of soft matter simulations, DFT also has approximations that make it very difficult to predict very accurately certain aspects.
Usually, we develop something like constraint potential. How can we specify your model? To carry out some benchmark simulation to.
Oh, for coarse grain or for molecular dynamics? Like DFT to molecular dynamics or molecular dynamics to coarse grain? Coarse grain models from. So I will talk a little bit about this in the next lecture, but the basic idea is you want to recreate the free energy landscape of what you want to look at. So if you have, let's say, a binding problem between two molecules, you want to capture the same kind of probability distribution with your effective coarse grain force field and your actual molecular dynamics force field. And there's many different approaches to that. I mean, probably hundreds by now of how you coarse grain, and everybody has a different say on how you do it. And that's the basis of many methods. It doesn't guarantee that you'll have the same mechanical features or transport features. So those are things to be careful about if you're making a prediction purely based on your newly developed coarse grain model. But generally, you need to map certain features such as the structural coordinates and the free energy landscape, and then you get some sort of approximate description. But it's not easy. It takes a lot of calculations.
I have one question. I mean, because hydrogen bond for all the results depend on the strength of hydrogen bond, basically of an organ system. And usually, in just to add to this question, DFT cannot reproduce this hydrogen bond formation very nicely. And can you comment that in your simulations you can really capture the approximate strength of these bonds correctly?
That's a very good question. I mean, the key thing is a lot of these models have been developed over 30 years, looking at many different experiments, looking at how these materials fold and how they behave at the equilibrium point. So I think in general we have a rough, good description. It's all empirical at the end of the day. It's a Leonard-Jones and a static, electrostatic case. We have a fairly good approximation, but it might turn out in 10 years that there are certain effects that we don't capture, let's say charge separation or that need a fairly more accurate description. So I think overall the trends you observe are all correct. Statistic values might change slightly, but
Trends may be correct, in the sense that the
I-
values may not exactly be equal to what you get in experiments, but maybe you catch the trends, correct?
yeah, I believe so. It's more comparative analysis of value. That's just my opinion.
So the basic behavior of the molecular bond has been tested with experiments. And the evidence reaches the classical experiment. They can test a simple bond at a time. So that's been very fast.
Because for this you need the electron density description, right?
Oh, yeah.
Describe the bonds and
Right,
breaking of
right.
bonds, and because this is most classical, so I was just wondering if, but if it's tested, okay.
Yeah, I mean, essentially, you don't get the same exact quantum effect. There's no way to do that with static electrostatic. But you've trained all of these parameters to the extent, the thousands of different values of parameters you have that effectively it captures experiments.
I think also in the soft material, soft system, there is the entropy effect dominance, the fluctuation dominance. So the quantum mechanics contribute really the energy barrier. That may be slightly off or here and there, but the fluctuation is so large. That may be dominating the whole thing.
Those are key. Those are very hard with DFT. So the best thing you can get from DFT is these energies and bond orientations and bond mass and these kind of things. But when you go into entropic elasticity, these kind of things, you need dynamics.
Yeah, I was wondering about these nanocrystals in the silk. How are they connected? Is it like folded crystals along a single strand of protein? When you have the big crystals and they break, like
Yeah.
they broke in half, would you get strengthening of that because then you get two smaller crystals, or will you have failure?
So the first question you asked is it folded onto itself or is it assembled such that two different?
No. I was more thinking like how are they connected to the rest of the silk?
Oh, you mean the crystals? Crystals are embedded in the amorphous domain, so they are connected. They are basically the same polypeptide strand, but certain regions of the polypeptide strand where this kind of let's say floppy material, all of a sudden they crystallize for the formation of hydrogen, and then the rest is just sort of semi-crystalline amorphous region. So they are connected covalently in that sense. But the distinction between the soft phase and the hard phase that gives this composite effect. And when you stretch it, these strands basically shear.
Yeah. But when you have the large crystals and they break in half, would you get strengthening of that because then you get smaller crystals, or?
Yeah, so if you have a smaller crystal, it's more shear type behavior. Whereas if you have large crystals, even with thermal vibrations, you have more banding. So even before you apply a force, you can have more banding, and it's more likely that you have a tearing open of the hydrogen.
Yep, but would that tearing lead to strengthening of the silk? Because then you get two smaller crystals instead of one.
Okay. Yeah, that's a good question. I've never thought about that. It probably depends, because if you...
That's why I asked how they're connected, because if they have like amorphous regions that separate them, I guess that would, instead of two crystals just very close, that would make a difference.
Yeah, I mean, you might get a sort of like a crazing that propagates through the material. So once you break that crystal, it may be in large force. Once you apply a large force, it might just cause a propagation, which I think is more likely, but it's just a guess. No one has looked at it. So, but I think that the people have considered that they would have sliding or opening of the crystals or breaking of the crystals, which might lead to the defect formation of larger crystals and chain, or in the other case, slipping and dissipation. So I think all of those small crystals are there. You can recreate them with tensions. But you do apply a certain level of tension when you're drawing the silk. So that if you draw it very fast, you have smaller crystals form. Maybe that might be the difference you described. At a certain force level, you can, when everything is soft and liquid crystalline, you can form smaller crystals by the applying a certain level of force. Does that answer?
Yeah.
Okay, thanks again.